Welcome back to Mega Mechatronics. We're going to look at slide carb tuning. This will be the slide carb tuning 101 video. So we're going to go into the workshop. We're going to get on the bench and I'm going to show you some things. And then we're going to get into the classroom to reinforce that information. And this was initially to help my friend tune his two-stroke engine. And it sort of snowballed into might as well make a global video to help everyone. So please enjoy and try not to fall asleep with my ASMR voice is what it is. All right, let's look at jettings. So here's a analogy here for your jets, okay? You got your pilot, slow jet. I'm calling it pilot. You got your main jet and your needle jets. And of course there's other jets, air jets and things like that. But like I'm going to say, we're going to get 80% there, and 80% is a passing grade, the last I checked. Okay, so ignore the capacity of these funnels. We're looking at the orifice here. Now let's do let's use our imaginations. And let me just say, you know the game where you stick a square peg through the square hole, round peg through the round hole, triangle peg through the triangle hole. Okay, if you don't get that game, then just turn this video off. I can't help you. Okay, so for everyone else, let's use our imagination. So which one of these funnels is going to flow faster? Let's say I dump in the same fluid and the same amount of fluid. Which one of these is going to flow faster? You are correct. The red one is going to flow faster. This is going to flow faster than this one. Okay, we're not going to get into the deep sciences. Again, we're going to get 80% there. So you need to quit making this so difficult on yourself. And that's why I'm making this video to help the world. I am helping my friend, and I'm not directing this at my friend because it sort of snowballed into making it a global video for the world. So I need to help out, or at least attempt to help out all levels, except for those who can't get the game of putting the square peg into the square hole, etc. and things like that. I can't help you there. You need to help yourself get to that level and then come back and watch this video. Okay, so this is an analogy for those jets: main jet, slow pilot jet, needle jet, and then you may, as you get more advanced, you're going to run into other jets like the air jets, the main air jet, pilot air jet, things like that. Okay, so we got the hole sizes pretty squared away. So let's set these aside and let's start looking at another concept. Let's say we're flowing a liquid through this funnel. What happens if I stick a pen in here? It's going to reduce the effective cross-sectional area. Just like this funnel has a smaller cross-sectional effective area. Just like this one also has a smaller than this cross-sectional area. Look at what we can do here. We can reduce the cross-sectional area. We have a slightly bigger cylinder here. Look at the cross-section. The area is being restricted. Look at that. I take the Sharpie. Look at the area. I mean, it's a little bit bigger than this, so it's going to flow a little less. And then we got this much bigger one. Look at that. We're blocking off. And now we're getting into the concept of this. Look at this taper here. Look at how it gets smaller. So if we take slices across here, they're going to be smaller diameters. Maybe this one's a little better to visualize that. We slice right here. That diameter of that slice is bigger than if we sliced it right here. But so look at this. Or maybe I'll move to this gray one and we can see it totally blocked off. And look at the area. It's getting larger, infinitely variable almost. Look at that. Until this comes out. And then we come back down. And it blocks off. And there's a tiny bit of area. So there'd be a tiny bit of flow. So when I pull this out farther, look at the area, effective area gets bigger. Therefore, you get more flow through it. Whatever, a liquid, an air, a fuel. In this case, we're looking at slide carbs. So here we got a slide carb. It's a WB02 VHST 28 millimeter. Hey, and that comes on this Polini Thor 202 paramotor engine. And look, I swapped on a Kian PWK 28 millimeter. Why would I take a perfectly good carburetor like this WB02, which is capable, proven? I'm not going to talk any smack about this. It works. It does work. The problem is I'm in the States, and there's no good source for needles and pilots or anything else, throttle slides, cutaway, different cutaways, things like that. You can find the main jets, and that's what everyone is leaning on too heavily, the main jets, where I'll show you the needle does most of the work. So let's tear into this and take a look at it. Here's your slide. Here's our needle. What I really like about this carb is how easy it is to pull the bowl. PWK can be a struggle with the factory bowl. Look at that, main jet. And so you can see how the floats are part of this assembly here. Makes it kind of handy. So we got our pilot jet here. So this pilot jet is going to have an effective area, just like these funnels here. So you can select different effective areas for that pilot, select different effective areas for the main jet. And down in here, you could see this pilot. I'm sorry, needle jet, excuse me. This is the needle jet with a cutaway to create some vacuum and help with vaporization. And you don't need to worry about that. Again, we're going to get 80% there, and 80% is a passing grade. So quit worrying about that stuff. As you get used to the pilot main needle tuning, then you can get more advanced as you want to optimize it more. And there's other considerations like flowable level and things like that, but this is a 101 beginner series, so I don't want to create confusion for you. And here's our air screw, or the fuel screw in this case. This would be our idle adjust knob. You can see down in there, that's going to interface with that edge and set your idle. So because this adjustment screw is after the slide, so airflow is this way, this is going to be your fuel screw. And like on the PWK, there's a screw on this side before the slide, and that's going to be your air screw. Okay, so if I put this slide in here, you can see that this needle, I'm going to need some tools to pull the needle out, but it does want to float in there. And you can see there's a straight section. I have a good pointy thing. It's random crap around here. So you can see there should see a little witness mark, a line. So that's the straight section and then the tapered section. So remember the example with the funnel, and I stuck that punch through it. This has a taper and that punch had a taper. Okay? So now imagine this is this orifice, this brass orifice that this needle is going into. So as you pull this out, like I was saying, if you take a slice here on the taper, that diameter is going to be bigger than the slice here on the taper, therefore increasing the cross-sectional area, the flow area for fuel to come through. So when the throttle is put in correctly, look at that. You can even see the needle through there. See that? So as it comes open, it opens up the orifice. As we close it down, it creates a restriction. So as you open the throttle more, you get more fuel flow. Because as you open the throttle, there's more airflow, so you need proportional amount of fuel to be added as you open that. Okay, so this is just a glorified ball valve or flow control valve. This is just a fully engineered flow control valve. So it's a metering device. You're metering fuel. Just like if you're servicing your car, you want to fill it up faster, you use a larger funnel, because it has a larger metering orifice right here. Okay? That's the concept. So quit making this so difficult on yourself. We're changing flow areas, effective areas of flow, and then all the tools are out there, and there's the tuning charts to get you in the correct area and help you choose which one do you need to adjust. Do you need to adjust the main jet for wide open throttle? Do you need to adjust the needle, taper, clip position, straight section diameter to get your mid-range? And then adjusting the pilot jet based on your fuel or air screw authority. So if you reach the limits of your fuel or air screw, depending on your carb, that tells you if you need to adjust your pilot jet up or down. So here's my little PWK tuning kit. I got my slow pilot jets, my main jets, and these are the needles I've developed to cover a large range. Here's my tuning chart. And I'm sorry, I know a lot of you feel entitled to my work. Okay, this video, I'm getting paid 0.02 pennies an hour for my work here. Okay, what makes you entitled to this? So what I'm doing, and what the philosophy of my channel has mostly been, is showing you figuratively how to fish. Okay, instead of giving you fish, I'm showing you how to fish. That's, if you go back in my videos, that's mostly what I do. And that was done on purpose because I put in all the hard work and I'm not getting anything in return. And my charitable service is to teach you how to fish. So I'm going to show you how I optimize these tunes from about verified negative 2,000 feet density altitude, density altitude, density altitude, density altitude. You must use density altitude. Okay, your MSL means sea level. Your altitude, your elevation means nothing. You need to use density altitude. So going back, I've verified these tunes from negative 2,000 to positive 4,000 feet density altitude. And this was done over the year in different conditions, and me setting up my equipment and instrumentation and doing the work in tuning the engine and finding the optimal needles, finding the optimal mains and pilot jets across those altitudes. And I did some extrapolations, and I've done some testing up to flying 8,000 feet. I didn't get a density altitude, but for sure negative 2,000 to positive 4,000 is pretty much dialed in. So if we come over here to my test bed, where I basically learned all of this, learned how to tune slide carbs with this motor. So from the factory, we have an EGT sensor. And the great thing about the Polini and the EGT with this engine is that they have a standardized location and a standardized sensor. So the probe model, make model, and the probe depth, and then the location of the probe. So the advantage of that is we can do apples to apples comparisons with other Polini Thor 202. It does not include any other engine other than the 202. That means the 303 does not count. So there might be a slight variation. I have not tested it. I know this engine and what optimal EGTs are, which also correlate with manufacturer suggested EGTs for cruise RPMs and wide open throttle, and that has also been triple, quadruple, however many times verified by other pilots with their independent testing. So in order for me to know for sure in my mind and not go off of hearsay, not go off the manufacturer, I installed the wide range, wideband oxygen sensor. You can see it's in the fat part of the pipe. Down in here. So I welded on a bung, and there's my oxygen sensor in that location. So having an oxygen sensor is explicit information on the air-fuel ratio. As far as what the optimal air-fuel ratio is for a two-stroke, I don't know yet. What I've been doing is targeting stoichiometric, the optimal air-fuel ratio at idle and cruise RPMs. And I'm learning by doing and just finding out, messing around and finding out for myself. And then if we look at the EGT sensor, this is where we can infer information about how it's running. And the bonus that the oxygen sensor doesn't have is this can help you optimize timing to a certain degree. Pun intended. And welcome back to the classroom. So I showed you some real life things, and now we should look at reinforcing that. And we're going to simplify things. We're going to use sketches. That is how I learn things. That is how I got to all these places. Through learning, struggling, trying to understand, lots of failing, lots of misunderstanding. I'm going to tell you a little story from when I was in the university. I went for automotive technician, mechanic, and one of the students had a show and tell. And this thing made me feel dumb. I felt gypped. But so the idea was he was going to make a lawnmower run on propane. And it's like, wow, how do you even do that? So he just had the propane tank hooked to the adapter through a tube to a little ball valve. And he cracked it open a little and started the engine and then got it revved up while adjusting that ball valve to get there. And then he tweaked that ball valve until it ran pretty smooth. And then he put his hands out and said, there you go. So I went into it thinking, okay, this is some complicated science. This guy is super smart. And he is smart and clever. Don't get me wrong. You had that 240 SX. I remember you. You probably remember me. You are a smart guy. And that was that, that increased my respect for you when you did that. But just personally, I felt gypped and disappointed in myself. I felt dumb that that's all that was. So he used a ball valve to adjust the amount of fuel flow into the carburetor to match the airflow. And he just used his senses to set the right ratio for that RPM and load of the lawnmower, spinning the blade. So there's that story. Okay, let's move on here. So figuratively, if fuel is your paint, and you're an artist here, then these things are your canvas, that carburetor's your canvas, and then you have your various brushes in the art of slide carb tuning. Brushes like needle jets, needles,
fuel jets, and main jets. That should say needle, but I guess it's sort of a jet system. I'm too lazy to go fix it right now. And then we have our Kihin PWK28. What I would suggest for best results is start with a quality part, a quality foundation. And what I really mean is quality controlled. So, in my opinion, getting something like a genuine carburetor from a genuine OEM maker like Kihin or Mikuni, that they're going to have a lot better consistency, consistent suppliers compared to some of the knockoff brands. There's going to be plenty of you saying the knockoffs work just fine, but I just gave you my thoughts and opinions on it. So there it is. You can have your own opinion, and I respect that, and I don't deny that you had good experience using a knockoff carb. Serious feedback of what is happening. So what is happening with your air-fuel ratio? That's what we're doing here. That's what all the fuel tuning is. That's all engine tuning is, besides the other, when we're talking about fueling for an engine. And that's what a carburetor does. It's the metering device for fueling, similar to a fuel injector and computer. That's going to meter fuel going into the engine or a carburetor. So feedback of how that is performing. So this technology is for optimizing the fuel delivery. It's what professional car engine calibrators use at the OEMs since the technology came out and became ubiquitous. And these are everywhere. It's not something special. And this technology is what professional aftermarket car engine tuners use. All of them use. You're not an actual engine tuner if you don't use a wideband, or you are a little anxious when you don't have access to one of these. And this is what DIY car engine tuners use. When you see someone say, yeah, I built this car and tuned it myself, some crazy race car or making a bunch of power, they used one of these, most likely, to get that fully optimized. Of course, we're going to talk about the other methods which are effective that don't use this technology, the exceptions to what I said. So I'm not being 100% truthful with you. I'm just trying to make a point here. So my opinion is, do not ignore this technology. My opinion is, you must not dismiss this tool. Common names are the wide range oxygen sensor, the wideband oxygen sensor, wideband 02, or written as WB02 sensor. And this is directly in real time measuring your air-fuel ratio. Direct, explicit, empirical, real-time data. And that is why everyone uses them. And you can get a full kit for about $200. That gets you 95% there. And then you got to do some, wiring and things like that. Crimp some eyelets on and hook up in your car and do things like that, or on your motorcycle or whatever. $200 gets you 95% there. And that's what concerns me, is you look at that and you'd trade 20 hours of your time for $200, or trade 40 hours, or give up the hobby completely over $200 and a little bit of effort. That's just my opinion. And some secondary feedback of what is happening, where we're going to infer, we're going to deduce from evidence and reasoning, rather than something explicit like a wideband oxygen sensor. So I had an EGT there. You saw it in the video previous. So just pretend, just go back and you'll see that EGT in my engine. So we can infer a lean or rich condition. We're not explicitly, we don't explicitly know, but we can infer, and sometimes you can infer pretty accurately. You can infer spark advance optimization, something that the wideband oxygen sensor can't do. And this can be accurate and it can be trustworthy if first you characterize that using something like a wideband oxygen sensor. So you can have a certain, 695 Celsius to 705 Celsius is about 14.3 to 1 air-fuel ratio. You can get that pretty close. And the one flaw, it's just something to point out, is it can give you a false high EGT lean inference, where you might think it's lean, where in reality it's too rich, combined with and or your spark advance is not optimized. Your spark advance is too retarded, letting unburnt fuel enter the exhaust and burn at the sensor, the temperature sensor, causing a high reading. Same with being too rich, that excess fuel leaving the combustion chamber is burning in the exhaust pipe, heating up the EGT sensor. And then for those who ignore this technology, dismiss the proper tools, there's the mess around and find out method, which is commonly used by beginners, the tenacious beginner tuners. And why I say tenacious is because if you're a tenacious beginner tuner, you're going to do a lot of messing around and a lot of finding out, and that it will eventually lead to you being the carb whisperer. The carb whisperer method here. And that's for the experienced and wise boomer tuners, or people who learned from the experienced and wise boomer tuners. And this is what you're going to see in a lot of the automotive carburetor areas. And this is that exception to those rules where I was saying everyone, all the professional tuners use a wideband sensor. This is that exception right here. And they deserve great respect that they put in the time and they're using their senses. They're using logic and reasoning and strong inferences of what's going on. They can get away without using an oxygen sensor or an EGT. And then there's the give up method. Buy your way out of this mess, never tuners. Or you give up the hobby completely. But what I mean by buy your way out, maybe you go to fuel injection and pay that premium. You go to an electric system. So that would be in like paramotors. There's 2 strokes. They do have 4 strokes. And they now, Vitorazzi has the EFI for a huge price premium. Or you can swap on your own fuel injection system, and that's still going to cost thousands of dollars to get the parts sourced. And this is aviation. You want it to be reliable. And so either you buy your way out or you give up, the never tuners. So we got our beginner tuners just doing the work, messing around, trying things, running your engine up and down, noticing that it's not running right, making changes, taking guesses, taking wags, and trying it and just doing it. And then we have our carb whisperer, the boomer tuners, the ones that have been around and they're experienced and wise and can do it. They are the carb whisperers. And then the give up, you're never going to figure this out. So you either give up or you find a way. You use your other skills and then you gather resources and then you trade those resources to get what you want, a good running engine. So close enough. Looking at this chart, it's close enough. It's a good starting point. It gets you 80% there, and 80% is a passing grade. So this chart, like I said, it's not perfect, but it's it gets the concept by enough for you to get a passing grade. And the main thing you have to keep in mind is that throttle opening at the bottom. Throttle opening, so idle and wide open throttle. And that's going to be a challenge for you to understand your throttle position, your throttle opening amount, so that then you can refer to this chart to understand where you need to make changes, where you're having trouble, and things like that. So there are methods and creative ways to accurately measure your throttle opening. So you need to find those ways. And up top we have the clip position, so that's referring to the needle clip. And so if I don't cover some of these things, let me point this out. This is a great example. Needle clip, I just gave you the key word. Clip position, that is another key word. So you go to a search engine, you go to YouTube, and you type those in, and you put a word like how to, explained at the end. Clip position, explained. Needle clip, explained. Put that in your search engine, put that in the YouTubes, and then learn about that. And come back here. That's how I learned all these things. It's a very long process. So I would pause this video, go down that rabbit hole, come back to this video. Here we got straight diameter. There's not a lot of information on that. And there's actually, with two-stroke slide carb tuning, there's not a whole lot of information out there. And I hope you all appreciate what I'm doing here. And let's move on. Needle taper. If you don't, I'm gonna show you these things. So if you still don't understand them, go down these rabbit holes and learn about them. We're not going to talk about the throttle valve cutaway because that's getting a little more advanced. And again, we're getting 80% to where you want, and 80% is passing. So that arrow down there, main air jet, we're going to talk about the main jet. And then we're going to talk about the air screw or fuel screw and the pilot jet, slow jet. And I'm calling it pilot. Calm down. It's my video. I'm just going to call it a pilot. Here, I showed you. It's also called a slow jet. So I'll probably be calling it a pilot. Maybe I'll throw in slow. So let's look at the pilot and main jet concept here. We have a side view, so we're looking top down at a smaller jet, and then we have a side view cross section. Here I have a slightly bigger jet. You can see that circle is slightly bigger, and the gap on the side view is a little bigger. So with the smaller jet, since we have a smaller hole, we're going to get less fuel flow. And we have a bigger jet. You're going to have, since the hole is bigger, everything else given the same thing, you're going to have more fuel flow. I hope that's obvious. So remember I was talking about the funnels? This is what I'm showing. This is the exact point of why I pulled out some funnels of different sizes. Use your imagination here. Smaller hole is going to be less fuel flow. Larger hole is going to be more fuel flow. The smaller hole has less cross-sectional area. The larger hole has more cross-sectional area. Now we're going to look at this pilot circuit. Very simplified view. Let's look at this air screw. So we have like the pilot circuit. That should not say fuel circuit. Pretty sure I fixed that. So we have our air screw more open, and you can see. Okay, I'm going to fix this. Here we go. On the left side, we have the air screw more open. Right side, air screw more closed. So because the air screw is more open, we have more air flowing in, and there's more pressure in that circuit, so we're going to get less fuel flow because there's less pressure. It's like if you're filling a tire with a portable pressure vessel, one of those portable tanks that hold air. If the tire's flat, you start filling it, it fills a lot faster because there's less pressure inside the tire. And as the pressure increases in the tire and gets closer to the pressure of the portable air tank, it slows down, the flow slows down. So we have less air on the right side, there's less pressure, so that means there's going to be more flow. Less pressure, sometimes called a vacuum. So you all know if there's a vacuum, things get pulled along a little quicker. So this is our air screw being screwed in a little more or screwed out, more open, more closed, and that's changing the flow through the pilot jet. And now we have our fuel screw. So let's say in the pilot circuit, there's no restriction on the air side. So that means we add a restriction in the pilot and the fuel side. There's not literally a screw in the jet. I'm just trying to simplify this for you. So there's going to be a screw in that pathway. So the fuel screw can be more closed. Fuel screw can be more open. So where the fuel screw is more closed, there's a restriction there. So we're going back to that concept of, instead of pressures in the air screw side, we're looking at less flow because there's less cross-sectional area. There's a restriction as compared to when the fuel screw is a little bit more open, you're going to get some more flow, more fuel flow. That's it. That's it. Okay, let's get a little more complicated into the scary needle. So a lot of us don't like needles. I don't like things being directly punctured into my purified bloodstream. So let's look at the anatomy of a needle and needle jet. So this would be like our needle jet. And then we have our needle. So like in that funnel example, I was sticking pens and paint markers and punches through the funnel. So I was representing the needle there, if you didn't pick up on that. And then looking at the needle specifically, we have the straight section. And also consider there's going to be a diameter to that straight section. And then we have our tapered section, because it tapers down. And again, that's where the effective area is almost infinitely, well, it's variable between the diameters of that tapered section as it's moving up and down. So let's kind of look at the concept of the needle clip. And we have our little throttle position now. So you can see that throttle position. You can, in our chart up on the upper right side, you can take a guess that's just under a third of throttle. I don't know, 30%, 25, I don't know, something like that. So if you look at the throttle opening, you could see clip position has authority around that area. So we have a needle part number ABC, and then we have needle part number ABC. So we have both the same needles, however, different clip positions. You can see the clip is higher on the one on the left, where the clip was lower on the one on the right. So what's going to happen to the fuel flow? We're going to have less flow with that higher clip position, because the needle's in deeper, and there's less, and the diameter rather is larger at that position where it comes out of that needle jet. And you can see there's going to be more flow. There's more area with that lower clip position because that raises the needle up. Some people say raise the needle, lower the needle. That's another way to describe the clip position. So we have the same exact needle, different clip positions. So it brings in that taper at a different time. Time being a throttle opening. It brings in the taper at a different throttle opening because it's giving you a different cross-sectional flow area. Less area, less flow, more area, more flow. So let's look at our straight section diameter, and you can see our throttle positions back down to idle. And if you look at the chart, you can see the straight diameter is more effective at that really low throttle position. So even off idle. So we have our needle jet, and we have needle part number ABC. We have another needle jet and a needle part number DEF. You can see they're both at the same height. But the one big difference you can see with needle DEF is that it has a smaller straight section diameter. And I hope you're seeing what I'm seeing. So we're going to have less flow with needle ABC. We're going to have more fuel flow with needle DEF because there's more area for the fuel to flow around it. Bonus, what about the needle jet size? Yes, that's another way, but that's going to be more advanced, but I'd just like to point it out. A larger needle jet will have more flow. A smaller needle jet will have less flow. So, you see what happened there? You can either change the diameter of the needle, the straight section diameter, or you can change the needle jet size. However, something like the Kean carburetor I showed you has a large needle selection. And you can even get very creative and adjust your own needles with some sandpaper. Now we're going to look at the needle taper. And again, check out the throttle position now. And so if you look at that chart up there, there's clip position, that's related to a needle. Straight diameter, that's related to a needle. And then we have our needle taper. You see how the needle, if you combine those top three, it covers the full range. It covers the full range of operation. And that's why I said before, the needle is the most important thing with the slide carburetor tuning. And that can have a great impact on how things are adjusted and how things are performing. So if you're just hyper-focused on changing the main jet and messing with the air screw or the fuel screw, you're missing out on a huge chunk. And even if you just change the clip position, you're missing out on that straight diameter and that needle taper at those higher throttle openings. So needle taper tuning. Here we have two different needle part numbers, part number ABC and needle HJK. And you can see they're at the same height, same clip position. They have the same straight diameter. However, there's a different taper. Same clip position. Got less taper on the ABC, more on HJK. Take a guess. You are correct. Less flow with the less taper. More flow with the more taper. And again, look at our throttle position. So we're engaging that taper section because we have the slide open a little more. As that chart shows, you're going to have the throttle opened up a little bit more to get that engaged. And then you can make your adjustments there. So let's look at the straight diameter and the taper sort of working together. We have this needle, so lower throttle positions, you can adjust the straight diameter. this straight section, that length of that sort of determines mid-throttle. And then the taper section is more of the higher throttle positions, and they all work together. And so let's say this is a baseline needle and give you some examples of going from a baseline to a different geometry needle and how that's most likely going to affect how things are running at what throttle opening. So let's look at this needle. We can see it has a longer taper, about the same straight section. So what this is going to do is going to enrich the higher throttle positions. And that mid throttle is going to get engaged a little bit earlier, but the huge impact will be at that higher throttle position with that more aggressive taper. So let's look at this one. We have a larger straight section diameter and that taper. So we're going to lean the lower throttle because of that larger straight section diameter. And we're going to enrich that higher, probably mid throttle as well, and enrich the higher position. Here we have about the same baseline straight section, a super aggressive taper. So that's going to be enriching quite a bit the mid and higher throttle position. And over here we have a small diameter, which is going to enrich in all those throttle positions. So when you get a needle set, you may want to invest in some calipers or something. A cheap set of calipers. I'm sure they work. So then you can measure these things and measure the differences. Because whatever charts they put on, I don't understand the charts that they give us on the internet. So these are the things I'm measuring. I'm measuring the diameter, the length of that straight section, and the length of that taper. And that I understood that a little bit more than the weird way that they characterize these and try to explain. I don't know, it's confusing. But this is the way I did it, and this is the way I understood and verified through independent testing. So in summary here, just about done. If you lower the clip, you're going to get more flow. You're going to enrich in higher clip, less flow. You're going to lean it out. Looking at straight diameter, smaller straight diameter, you get more flow. So you enrich in. Bigger straight diameter, you get less flow. So you lean it. Looking at the needle taper, more taper, more flow. Less taper, less flow. Larger main jet, more flow. Smaller main jet, less flow. So more flow means more fuel, means it's more rich. Less flow means less fuel, means leaner. Got our larger pilot. Larger pilot has more flow. Smaller pilot, less flow. I hope you are seeing a pattern here. With the air screw, when you screw in the screw more, you get more fuel flow. When you back the screw out, you get less fuel flow because the air screw is bypassing air. So if you screw it in, you're reducing the air, you're going to get more flow. It's another way to think about it. Or if you have that fuel screw, it's the opposite of the air screw. So the less you screw it in, less of a restriction you're going to get more fuel flow. And then if you screw the fuel screw in, you're going to get less flow because there's a higher restriction. That's it. So you want to go out there and do it. Either grind away so that you can get to that whisperer level. So that's going to take a lot of work. Or you can save a bunch of time and save a lot of frustration by going to a wideband oxygen sensor and even an EGT. But that wideband, that's the key. That is the cheat code to figure this out, where you need to make those changes. So you got your wideband hooked up. At idle, you're not running good. You're running lean. You're running way too rich. So then you look at that carb chart and you make an adjustment there. Okay, mid-range, you're cruising around. You're at a certain throttle position that's more than idle. So then and it's not running right. You got your wideband hooked up saying, hey, I'm too lean. Hey, I'm too rich. Or, hey, I'm just right. But if, let's say you're too rich, so maybe you need to raise the clip position and which lowers the needle so that it doesn't engage the taper as soon in that throttle position. And go the wide open. I didn't even cover wide open throttle because it's so easy. You just hold that throttle wide open. You read the wideband gauge. You want whatever, 12-to-1 air fuel ratio. So if you're 13-to-1, you need to add fuel. How do you add more fuel when you're wide open throttle? Refer to that chart. You see that the main jet is the main go-to for that watt position. So then you increase the size. If you increase the size of the main, you increase the fuel flow. Woo! Yeah. That's all it is. That's why I'm getting frustrated, because that is all it is. It's a metering system. I understand, yeah, the challenge is knowing what to change. And that's why we have that chart, that this chart right here telling you what to change based on that, how it's running at that throttle opening. And then there's that wideband O2 myth that you're going to kill the wideband instantly. The wideband is just not even going to work. You're going to be running it for 5 minutes and it just dies. That is a total lie. Unless, let's say it's running absolutely pig rich at the edge of it's just misfiring like crazy, and you run the engine like that for a half hour with the oxygen sensor. What do you expect to happen? That's going to happen to any engine, not just a two-stroke. That's abuse and why you're killing it. And also, in this aftermarket world, it's a wearable part. They're not going to last for 100,000 miles. What do you expect here? We're tuning engines. We're making power. We don't care about longevity. We care about our machines running optimized, making the most power, running the smoothest, and not letting us down. Winning races for those race guys. So that is a myth. And then here's the secret. You remove the oxygen sensor when you're done with it, after you get that tuned for that density altitude, and you put the plug in there, the bung plug. So you got an O2 bung, you remove the sensor, and then you put a bung in there. So then if you have a big weather swing, it's fall, you can retune it. And then once you find the tunings for that density altitude, all things the same. If you're always making changes to the engine, then you have to check the tune. But once you get that density altitude, and you verify it another time with that oxygen sensor, you can remove the oxygen sensor completely and just run the engine based off your tuning information. And better yet, have that EGT as that secondary, more robust system, that there's less of a myth saying that your EGT is going to just stop working after 5 minutes. So then you can run that EGT all the time and get a really good idea after you ran that wideband and set things up. So you say you're wide open throttle, sustain, you're climbing, you're on a hill climb or climbing up in a paramotor, and you get a certain temperature and you're 12-to-1. Let's say 12.5-to-1 is your target, and you have a certain temperature. That temperature is now gold. You can write that in stone. All things the same. You didn't make modifications to the engine or change the fuel. You would want to re-verify that. So then next time you're climbing full throttle, you can look at your EGT and see how you're doing there. Okay, that's it, and I hope you got something out of it. I'd recommend rewatching the video, and then you can kind of start connecting the dots. Go play around with your engine, get that wideband sensor installed, come back to the video, watch it again. And then there's other great resources out there. Slavin's Racing is one. Michael Forrest, both on YouTube. So type in like Michael Forrest two-stroke, and then you'll find their channel. Go to their channel, and then Slavin's Racing two-stroke. Search for that on YouTube, and then you go find the YouTube video. You go into their videos, and you go to their search bar, and you type in like tuning. Okay, this is how I learned. Is it because I know how to search for things and keywords? Maybe that's it, but I just gave you the clue. So there's keywords out there, and then you use those keywords and do searches. And I wish you the best of luck. And again, you may have to re-watch the video. I'm sorry. And pro tip here, you can set the speed to like 1.25x on YouTube or 1.5x so that I'm speaking a little quicker. Fortunately for other people, me speaking slower is beneficial to their learning. So leverage that warp speed speaking